Good morning, everyone. My name is Nathan Heston, and as you trickle in, I'd like to introduce my colleague, Daniel Moyer, joining me today, freshly back from Paris. Welcome, Daniel.
Thank you, Nathan. Good to be here.
Glad to have all of you here as well. I am experiencing a little bit of technical difficulties on my side. I cannot see the Q&A, but Daniel, I hope will be able to do that. And so I encourage you to use that to ask questions throughout this seminar. We love giving these seminars, and we really enjoy the questions that you bring forth, and we'll try to answer them all. This is a NABCEP accredited training, so if you're here to get those continuing education credits, please stay through the end. Send us an email. We'll show our email at the end of the talk with your name as you would like it to appear on your NABCEP certificate, and we will get those generated for you. Typically, we give 1 day before we do those, just to allow you time to get a response back to us. If you're interested in a recording of this training, everybody who registered for the training gets a copy of the recording. We'll send that out after the training is complete. We'll also be sending out the slide decks and notices about our upcoming trainings. So once again, welcome everyone. This is a NABCEP certified training, and we're happy to have you here. The topic of today's training is on Battery Chemistry 101, and I'll get into some of the specifics of the battery chemistry that we use and why. Daniel, would you like to talk about this program on April 11th that you'll be attending?
Yeah, thank you, Nathan. So for anybody who happens to be in California, who happens to be in Northern California, Green Tech Renewables Santa Rosa is going to have an open house and battery summit. So what you're seeing on the screen is a QR code that allows you to register on Green Tech Renewables website to get a free ticket to attend. And we're going to be there. We're going to have a table there, and anybody who shows up will have free hats, shirts, whatever you guys want, we'll have it for you. In Santa Rosa, California, which is just north of San Francisco, April 11th, 10 a.m. to 3 p.m. That's this Thursday.
Thanks for plugging that, Daniel. For those California installers that are on here with us, I encourage you to maybe attend, speak to Daniel, bring him some questions, give him some tough ones. I'll give a free sweatshirt to anybody that goes and stumps Daniel. So welcome. So the topic of today's training, again, is Battery Chemistry 101. We're not going to be going through chemical equations here, but we are going to be talking about the different battery chemistries that can be used in lithium-ion batteries. And we're going to talk about why we use the battery chemistry that we do and what the benefits are to that. So one of those benefits of using lithium iron phosphate battery chemistry, and I'll explain where that name comes from shortly, is a very enhanced cycle life. We can get cycles of 10,000 out of these batteries. If you're familiar with lead acid batteries, right, you might get 1,000, 2,000 on a good set of deep cycle cells. We're talking about 10,000 cycles here, 80% depth of discharge. Okay, so if we do 100% depth of discharge, those number of cycles shrink. And I'll show a slide where we can show you the approximate number of cycles we expect you to get based on depths of discharge. This enhanced longevity of LFP cells and, coupled with our BMS, our sophisticated advanced BMS that I gave a training about last week, allows us to give a very aggressive 15-year warranty. And that's a true 15-year warranty. No limit on the number of cycles, no limit on the depth of discharge. And we also guarantee a 70% end-of-life capacity after 15 years. That means we're really giving you a solid warranty here. No loopholes in that. And this is on all of our communicating batteries. So our communicating batteries that you're going to be seeing today, I'll be going through those. So these three batteries on the screen are manufactured in California. The battery on the left side of the screen, there's an AmpliPHI battery. And then the one to its right labeled 4.9 is what we call our SimpliPHI battery. Those come in 3.87 kilowatt hour blocks on the left one. And then the SimpliPHI comes in a 4.98 kilowatt hour block or module. Those batteries have a 15-year warranty on. The PHI battery, we don't have communication enabled on this battery. It still comes with a 10-year warranty, the same kind of terms of that warranty. And then both the Phi and AmpliPHI batteries can be combined and put into our what we call access cabinets or boss cabinets, which will hold either 12 batteries or 6 batteries plus an inverter. And so again, we're making these here in California. If you are a California-based installer, you can apply for the self-generation incentive program. And because the Phi and AmpliPHI are on that approved California manufacturing list, you can get an extra 20% discount off those battery install costs. And we've listed the utilities that are participating in this program here in California. I realize many of you are not installing in California. And you may or may not know the history of Briggs Stratton and SimpliPHI Power. Briggs Stratton has been a long-time engine manufacturer and equipment manufacturer in the US, 115-year legacy, really long-running company. SimpliPHI has been around for about 15 years, making batteries out here in California, Oxnard, California. And a couple of years ago, Briggs Stratton acquired SimpliPHI Power. We're one of 2 companies that manufactures both lithium batteries for energy storage systems and generators in the US. And we have options for integrating generators into battery energy storage systems. We also are a company that does our engineering and a lot of our manufacturing and definitely our assembly here in the United States. So why Briggs & Stratton? Designed, engineered, manufactured in the USA. We have a manufacturing plant in Oxnard, California for our batteries. We have a number of manufacturing plants for our engines, generators in the US. We've got a company outliving 10-year warranties. We now have a 15-year warranty based on the proven success of our AmpliPHI and SimpliPHI batteries. Again, 10,000 expected cycles with these batteries. They're really designed for longevity. Tested and proven by the US Department of Defense. We have a history of providing batteries and really introducing the US military into that change from lead acid into lithium batteries. We are a heavily tested battery company. We focus on safety, and we have 9540, UL 9548 tested LFP battery chemistry. Compatible with many leading inverters. We plug SolArcs very heavily, but we also have a lot of installs with SMA, Schneider, Magna, many other leading inverters and charge controllers. AC and DC coupling, C/2 rate. In fact, we've even improved that on our latest 6.6 battery offering, which we'll be talking about soon. So a C rate describes how quickly the battery can charge or discharge. It's typically referring to the current, but really this is just an expression of how quickly you can get the energy into or out of a battery. C/2 means you can charge or discharge in about 2 hours, which is a pretty quick charge-discharge cycle. That allows these batteries to have a fairly high power output for their overall size, their capacity. So the energy storage market is growing. You probably know that. This is the age of batteries. Many customers are choosing to install batteries on their houses. And this figure, this expected growth of 33% by 2027 of solar installations having batteries coupled with them will probably grow. I believe this number is from before NEM 3.0 took in effect here in California. And we're expecting similar disincentives for using the grid in terms of net energy metering. Now it's no longer net energy metering, but net billing. And Daniel gives a great talk.
And Nathan, I wanted to just make a point that you are allowed to add a battery to an existing NEM 2.0 system and not lose that favorable interconnection agreement. So that's really exciting. Additionally, you can also add a battery and receive the ITC, the investment tax credit of 30%, and not have to even pair it with solar if you do have a situation where that is the case.
Daniel, so great to have you back. I actually had a question on that yesterday, and I was thinking I can't wait till Daniel's back so I can ask him, can you add, I've got a customer who'd like to add a couple of solar panels to a 20-panel array just to boost his overall capacity a little bit. Can you do that and maintain your NEM 2.0 or status? Yes.
Well, it depends. And one of the unique things is that if the inverter has any headroom, what I mean by that is if you have, say, a 6 kilowatt inverter and you got 6,000 watts of solar, you can add additional solar to the system and not lose that favorable interconnection agreement here in California specifically. You're going to get some inverter clipping, but that's okay because you're still going to get a lot more morning production and a lot more afternoon production as well. So
as long as you have some headroom on the inverter can take that extra connection of solar panels. You can still maintain that NEM 2.0 status. Can't upgrade the inverter, but could potentially just add more solar panels and deal with a little bit of loss due to clipping, but you'll overall have more production earlier in the day, longer in the day.
Yes, exactly. And a lot of times, especially when people are on time of use, and this can apply to everywhere in the country, that that's when you want to be producing. That's why we're seeing a lot more west-facing arrays. Is let's self-consume the home when power is more expensive, with a lot of these time of use rates that are starting to come across.
Of course, batteries are going to give us that option as well to it changes the equation a little bit once you do add batteries, but absolutely understand west-facing arrays. You come home from work, want to use that electricity. Electricity is expensive. You benefit a little bit more from having a west-facing array. So I'm not going to spend a lot of time talking about why the market is growing, but suffice it to say that more and more people like Daniel and I are working from home, want to have access to continuous power. Infrastructure, as you know, is aging. We've had a lot of problems with fires in California and the utilities being held responsible for those, ultimately the investors. Climate-related disasters, of course, we're being told are growing, right? And then a big one here is people are consuming more electricity. EV market adoption, the vehicle growth is something that's going to create strain on the grid. And even strain on individual homes, right? As people are looking to run high amounts of current out to the garage to charge electric vehicles, they're going to be needing to upgrade their services to do that. The benefit of having electric vehicles come onto the market is that they can be programmed to charge overnight when electricity rates are cheap and when the demand is down on the overall grid, helping to kind of stabilize production a bit. Growth of clean energies, energy solutions. Certainly, there are plenty of people wanting to have clean, renewable energy powering their home, their devices, their electric vehicles. So applications of batteries allow us to do a lot of things, like have backup power, save on our utility bill, generate that electricity during the day when the sun is out, consume it, as Daniel was saying, self-consume by using that in the evening times. Of course, when you combine storage with renewables, it gives you access to do many more things as what I was just saying, but also even just things like peak shaving, where you can combine that power coming from your batteries and reduce the amount that you're drawing from the grid at specific times. Of course, there are many customers that are still going off grid. I'm going out to a customer site here locally with one of our elite installers today to check out an off-grid site. And then, of course, there's generator optimization. If you are using a generator for backup or even for primary power, you can add batteries to it, run that generator for a short amount of time, charge those batteries up, and shut that generator off quickly, preserving fuel, preserving the lifetime of your generator, reducing the amount of maintenance you need to do, reducing the noise, consumption, etc., fumes. So the topic of today's training is battery chemistry. And we're going to start off with the basics and go through the differences. There are lots of different types of lithium batteries. They are not at all the same. And typically the way they vary is on the positive plate, the lithium collector when a battery is discharging, something we call the cathode of the batteries. And they vary by the type of metal oxide layer that they use to house that lithium. And those metal oxides, like the lithium is very stable there, and that's where the lithium goes as a battery is discharging. It's one of the driving forces of a lithium battery. So the variations on the left side of the screen under battery chemistry are typically just differences in what the cathode is, with the exception of the last one, the lithium titanate. That's a different anode, or the negative plate of the battery. So what are the differences? Why are there so many different ones? What are the benefits to each one, etc.? So I've mentioned we use LFP battery chemistry because it's a safer chemistry It's less prone to things like fire. It is a little bit heavier, and we'll talk about the energy density here in a second. So we use lithium iron phosphate. Other common battery chemistries like NMC. NMC is still common on homes. Like Generac has a power cell. It's an NMC cell. All of the original Tesla Powerwalls and Powerwall 2s were NMC. Now Tesla and others are switching over to LFP, so Powerwall 3s and LFP battery chemistry. Better overall battery chemistry LFP is for home energy storage. Let's talk about why. So I pulled this morning from website dragonflyenergy.com, and it compares LFP and NMC chemistry, since these are the two principal chemistries used in home energy backup systems. As you can see, you get similar performance out of both of them. The cost is similar on these two. More safety with an LFP battery. Specific energy refers to how much energy you can pack in a battery per kilogram. And NMC does a little better there. You can make a lighter battery that has the same amount of energy as an LFP battery. However, that's not really that important for stationary batteries like those used in homes. And so I would argue that on all of the important points, especially the lifespan, right? Lifespan and safety, and LFP is the better battery chemistry, and that's why everybody is switching to it. SimpliPHI has a 15-year history with LFP battery chemistry. We've been refining our batteries year after year, which is why we can get safer, longer lasting batteries than our competition. So we're using lithium iron phosphate, we're using cylindrical cells in these batteries, and inside the cell, it looks something like this. Again, we're not going to go through all the details and point out all the different things, but at the top of the cell, you have an aluminum layer, and that is folded over. Those extra long tabs are folded over from that positive side of the cell. On the bottom side, you have a copper layer, and so you have this copper and aluminum foil, which are sandwich a separator layer, and that separator layer prevents direct contact between those. The copper and aluminum are both coated. The aluminum foil is coated, in our case, with LFP, lithium iron phosphate, and then the copper foil is coated with a graphite layer. And in a charged battery, the lithium ions reside in the graphite side. In a discharged battery, an empty battery, the lithium has moved over to where it prefers to be, the metal oxide side. Now, the separator layer that goes between the graphite and the metal oxide side, in our case, the iron phosphate, does not allow electrons to move through it. Also, what you cannot see is within the metal oxide layer, within the separator layer, and within the graphite is an organic electrolyte solution. And an electrolyte solution is just basically a salt solution. It's about the consistency of something like diesel fuel. It is organic, so it can burn. And it contains the lithium salt, and it's what allows the lithium to be mobile. Now, the separator layer prevents electrons from moving through it. So the only way for the lithium to go between the metal oxide and the graphite side is to have the electrons go around the outside. So if I looked at charging this battery up, a discharged battery, most of the lithium will be over here in the metal oxide cathode side, the positive side. But if I take a charger and I pump the electrons away from the lithium atoms will become lithium ions. The electrons will be pumped over to the negative side of the battery, and that'll draw the lithium ions through the separator layer over to reside inside the graphite layer where they've met their electrons. That would be a charged battery. If I then have that charged battery and I change this charger for a load and discharge the battery, I can allow the electrons to flow through the outside circuit. The lithium prefers to be in the metal oxide layer, and so lithium ions here will draw those electrons over. That's what creates the current to discharge your battery. So in a nutshell, that's what's happening. Now, in a cylindrical cell, the way that we do this is we have this copper layer extend down below a little bit farther than the aluminum foil on the other side. So the extra tabs there are bent over on the top and then spot welded to, and then the extra tabs of the copper on the bottom are bent over down at the bottom. And that's how they form one of these cylindrical cells.
Nathan, let's
Yes,
go back a slide, please. And
sure.
I just want to encourage everybody on the call today, use the Q&A. There's a Q&A button usually at the top or the bottom of your screen. Go ahead and put in some questions or comments. Whenever we have questions and comments, it really makes these talks more interactive and enjoyable for everyone. But I have a question for you, Nathan.
Sure.
I'll put you on the spot here. I've heard that sometimes you don't want to fully charge a battery. And I've heard that maybe extends the life of a battery. Why is that you wouldn't necessarily want to fully charge or fully discharge a battery, and that would help extend the life of a battery?
So that's a good question. It depends on what you mean by fully charge and fully discharge. You do want to make sure you get a battery all the way to the state of floating occasionally to allow the BMS to balance the cells. So regular battery modules are made up of large numbers of cells, and those cells are arranged in blocks, and then those blocks are arranged in series to produce a 48-volt battery, for instance. And if you do not get to higher states of charge, your BMS does not get the opportunity to balance the cells. That being said, you do not want to hold the batteries at high voltages for long periods of time, because that can cause reactions that are unwanted, which can cause breakdown. I'm assuming, and I'm a little bit out of my element going too far here, but can cause breakdown of things like the electrolyte and reduce the overall longevity of the cells. On the discharge side of things, fully charging and discharging cells also causes another challenge within the nanocrystalline structure of the graphite and the metal oxide side of the cells. So these are nanoparticles that are deposited on the films, as I mentioned. But when they absorb lithium, they swell up, and when they release lithium, they decrease in size, kind of like wood getting wet and increasing its size, and then getting dry and decreasing its size. Well, just like wood will split with time if you get it wet, dry it out, get it wet, dry it out repeatedly. Similar things can happen to the metal oxide and the graphite side. So that swelling and contracting, overswelling, overcontracting is what would, I presume, cause much of the damage in high voltages and extremely low voltages. Because essentially what's happening in high voltages is you got very large amounts of lithium in the graphite side and low in the oxide side, and then at low voltages, completely discharging the battery, the graphite is essentially empty, and now we're putting almost all of the lithium into the metal oxide side. So I hope I did that justice. Typically, we don't get tons of questions when I get into this chemistry stuff. But let's get into the things that are going to matter for people as well. Let's talk about one of the other reasons we use LFP. We also believe, okay, so there's safety, there's toxicity. We don't use cobalt-based chemistry, which many of these other chemistries contain cobalt, because it's a rare earth element. It's a toxic element. It's typically mined in Central Africa, Congo, for instance, where mining practices are quite questionable. There are other challenges, of course, that result from using this chemistry, and that's the increased likelihood of things like off-gassing and fire. Again, we're a company that bases our battery chemistry and our choices on safety and longevity. Now, it is important to point out that none of these batteries should go into a landfill. None of them are landfill safe because of the lithium that is contained within them. So you do want to make sure you recycle them. And there are plenty of recycling programs that are out there. These battery cells that come from batteries get upcycled. We have a scooter company, I believe, that often takes our recycled batteries. And then there are companies like Redwood Materials, who I have a former student working for them now, that are buying used batteries to extract the lithium and other components for recycling purposes. So thermal runaway, as I mentioned, batteries are often composed of many types of cells, many numbers of cells, sorry, not types, many numbers of cells. And it is possible, if you get damage to a cell, you can imagine maybe there's a car accident, or maybe there's just an internal failure, like was happening with the Galaxy Note 7 that's on the phone. And I feel bad continuously picking on this phone because there are other things, other issues associated with fire, but this is one pretty common knowledge to many people, that about 10 years ago, this Galaxy Note 7 was banned on flights because of the possibility of going into thermal runaway. So thermal runaway is when one of the cells has some type of short circuit failure or damage, and that'll cause that cell to discharge internally, and that discharging internally can produce a large amount of heat. That heat can eventually, if unchecked, result in that cell getting hot enough to release that organic electrolyte that's inside there. If one of the cells gets very hot, then it's possible that the cells around that that heating cell can also get hot enough, and you can essentially get a chain reaction if this is unchecked. And that chain reaction can really lead to a battery fire. And you've probably seen images of electric vehicles after maybe a big crash being in one of these thermal runaway events in which there is a fire. These are typically NMC batteries that you're seeing doing that. And that's one of the reasons why Tesla and Rivian have switched over to using LFP in the majority of their vehicles now. But I want to point out that thermal runaway, we essentially have no risk of unmitigated thermal runaway in our LFP cells. And our 9540A tests that we publish to show that. What does happen in thermal runaway in NMC cells is you get to higher temperatures and you have a much more rapid release of energy. So overall, the temperature of an NMC cell when it goes into thermal runaway, or an NMC battery when it goes into thermal runaway, is typically higher. The overall temperature, as you can see on the screen, will reach temperatures like 675 Celsius, which is quite hot. And thermal runaway can happen at lower overall thresholds, like 170 C for an NMC battery, versus an LFP battery, you have to get it much hotter to get it to go into that thermal runaway off-gassing event. And so we have, there's a lot of examples online. A typical test that is done is a puncture test, in which you puncture a cell and you look at what happens when those layers get internally shorted out. This is one that we've shown a number of times here. It's a video of Will Prowse, who's a prominent battery tester and YouTuber. And he punctures an NMC cell, and what you can see is that battery goes into thermal runaway and results in a fairly high energy off-gassing event with an NMC cell. But with an LFP cell, a very similar pouch LFP cell there, he had to puncture it many times to even get it to go into thermal runaway. Maybe 8 or 10 punctures he did with a drill before he could even get it to off gas. And as you can see, it just slowly discharged that overall energy. Nathan, it's just an example of the safety of LFP. Yes.
So let's please go back one slide.
Sure.
So I have a question, and then we also have one that came into the chat. My question is, what are some of the advantages of pouch cells over cylindrical cells or even prismatic cells? That's my question. And then let's go ahead and address Mike's question here in the chat. And I'd encourage anybody to comment or add a question. Mike says, recently a supplier has offered some SimpliPHI 3.8 kilowatt hour batteries that were new, but had been stored, in a new condition from anywhere from 2 to 5 years. They were at a great price, maybe half the price. The supplier, I'm assuming distributor, tested them by charging them and discharging them and recharging them again, and concluded that they had some usable life remaining. I'm assuming that they did a capacity test. What do you think about the batteries' remaining life if they've been sat in storage for that long? And again, any other comments are appreciated. So let's go ahead and address Mike's question first, please.
Yeah, I think that's a great question, Mike. And to be honest, unless these batteries were discharged down to very low levels, they are probably perfectly fine. Batteries experience more wear on batteries experience more wear and degradation when they are cycled, especially when they are maintained at high states of charge for a long time. So at half price, I would think you would get more than your money's worth. out of batteries like that. You can always run a capacity test and check, can I get 3.8 kilowatt hours at a C/5 discharge rate? So if I discharge it at about 1,000 watts, how long do I get? How much energy do I get out of it? And so I would encourage you to review their capacity tests, but for the most part, I would expect that these batteries are still in pretty good shape. Now, if that warehouse was wet, I would then start to question things. If there's high levels of humidity, that kind of thing, you might see some calendar aging in those batteries. So in the West here, it would be a minimal concern for me, where less humidity in the overall air. In a warehouse, as long as they were kept dry, they probably have a lot of life left in them, certainly half of it. But again, you should be able to test that from the overall capacities, and I would expect you to get your money's worth. So hopefully that's a reasonable answer for you. Daniel, on pouch cells, there's some big advantages to pouch cells. I mean, the fact that you can pack a large number of these cells quite tightly together, for instance, just from the shape. They are cheaper to manufacture. You need your BMS equipment for these pouch cells, for instance, can be simpler. Your balancing, your combination of cells, so not having to do all these welding. Occasionally, spot welding can introduce defects into batteries. On the other side of things, there is more expansion and contraction with pouch cells, and technology keeps changing. I keep getting, Google follows my searches and keeps telling me, that we're going to soon have, electrolyte free, solid state electrolyte, essentially, batteries on the market soon. And when you try to read about that, right, there's, a large fraction of the research community doesn't think the technology's ready. But there's a huge amount of progress being made in batteries, and I think it's impossible for one person to stay completely on top of everything that is happening. But thank you for the question, and let's jump back into the safety. I have a lot of slides I want to jump through. This one is talking about, this is done by Sandia National Labs in New Mexico. This is their tests on different battery chemistries looking at the safety. One of the things I'm going to highlight is, so it's a normalized heating rate here, which means this is how quickly the battery's energy was turned into heat. So how quickly the battery, and so this is per kilogram essentially, or per mass, to normalize for basically different cell sizes and cell weights, battery weights, etc. But when you look at this graph, you can see that the LFP batteries are just essentially on the horizontal axis. They don't even show much. NMC cells, you're spiking it over 200. The NCA cells, nickel, cobalt, aluminum oxide, and lithium cobalt oxide cells are getting the most kind of rapid creation of heat in a thermal event. So if you zoom in, you can see that the lithium iron phosphate cells jump up around 1.5. So almost 100 times less, over 100 times, about 100 times less than the NMC cells in how quickly they're producing heat. And that's what makes them safer overall. It's a much slower production of thermal energy in a thermal runaway event. I created this slide today to try I got another question today about batteries not hitting their overall 56 bulk voltage. So I want to point out that there is a charge cycle for batteries which consists typically of two phases, what we call bulk and absorb. And if you have some renewable energy resource like solar, you might float your batteries as well in a third cycle where you just hold it at constant voltage again. So this charging cycle begins with a constant current bulk phase. And so that constant current, we set a maximum bulk current, and our batteries is C/2. So a 75 amp hour battery like our AmpliPHI or our PHI battery will be charged at 37.5 amps, half, C over 2, half of its overall amp hour capacity. And so if I'm charging at constant current, I'm charging as quickly as my batteries can, and I will see that voltage creep up higher and higher as my state of charge approaches 100%. It's not going to quite hit 100 in the bulk phase, but we stop bulking when that voltage gets up to 56 volts. At that point, we just hold the voltage at 56 volts constant, and you'll see the current trail off as the battery gets to 100% state of charge. So we start with a constant flat current, and then that current tails off as that battery reaches 100% state of charge. Typically, the bulk cycle, if your battery is down at maybe 80% or 90% discharged, that will be just under a couple of hours for the bulk cycle, and then just 6 minutes on the absorb cycle to top that battery off to get it fully charged. However, people will often complain, I can't get my batteries up to 56 volts. If you charge more slowly, that voltage won't go as high. And the reason for that is there's the resting voltage of a lithium iron phosphate battery that's fully charged will only be about 53 volts. What you're seeing on the screen is the charger's voltage. But if you're not charging at a fast overall current, if you're doing a slower charge, your overall voltage won't go in as high. And that's because when you're pushing current into a battery, there's a loss of voltage inside the battery, right? In addition to the voltage across the cell. And so a loss or a gain of voltage, a gain when the charge is coming into the battery, and a loss of voltage when that charge is going out. So on a discharge cycle, I will lose some voltage as the battery first starts to discharge. So as your charge cycle ends, your batteries will probably sit about 53 volts fully charged. So the dark line here is the resting voltage of the battery when current's not flowing into or out of. The green lines are when it's in a charge cycle. And if I'm charging it quickly, I expect the green line to be much higher, a couple of volts, 2-3 volts higher than the overall voltage of the resting cell. And if I'm discharging quickly, it might be 2 or 3 volts lower. So a battery discharging very quickly, even though it might be at a 70% state of charge, might be close, under 50 volts. So I hope this helps a little bit. And it has to do with the direction of the current flow. So when current is flowing into the battery for a charge cycle, you'll see an elevated voltage. You may never hit 56 volts. That doesn't mean your battery's not fully charged. If you take any battery and just charge it at 54 volts for a very long time, it will become fully charged. So this is what that charge cycle looks like at a C over 2 rate. You're charging, voltage comes up, you hit 56, you maintain it at 56 for 6 minutes, and your charge cycle is complete. This is called the bulk part of the cycle, constant current section. And the absorb part is when you're at a constant voltage, a decreasing current as that battery fills up. So the recommendations are on our screen. Again, I'll provide these slides. If you are going to have a renewable energy source and your battery's fully charged, like mine often do, float them at 54 volts. That'll keep them topped off at 100% state of charge, but not introduce any damage. You don't want to float your batteries at 56, 57 volts. That will damage the batteries over time. Those elevations or decreases in the overall voltage also depend on the temperature of the battery. So a cold battery discharging, you're going to see, depending on how cold it is, it influences the viscosity of the electrolyte, and you'll get an overall increased internal resistance at lower and lower temperatures. So if you're discharging in really cold conditions, at a very fast rate, you might see your batteries dip below 48 volts, even at 50% state of charge, right? It depends on how quickly you're discharging. So when you're trying to discharge batteries under cold temperatures, you'll often see that the batteries can't quite produce that energy without dropping to a lower voltage. This is why cold cranking amps matters for lead acid batteries, for instance. I need to change the battery in my keypad for my garage door opener right now. In the cold mornings, it won't work, but as soon as the day warms up in the afternoon, it works fine. And I know that battery's just about out of charge. That's non-rechargeable one. So, there are challenges associated with charging lithium batteries, all lithium batteries with electrolytes in cold temperatures. And this has to do with the growth of what we call dendrites. So if you charge in extremely cold conditions, that makes it the conditions much more suitable for the growth of things called dendrites, which are solid lithium deposits. So that reduced permeability of the lithium into the graphite layer and the reduced mobility of the ions in the electrolyte will end up causing buildup of solid lithium on the anode layer of the battery, and those growths can look like dendrites, which I believe literally the translation here is branches, right? And so those branches can eventually puncture a separator layer. So if you charge batteries in cold temperatures repeatedly, especially at high rates, you will drastically decrease the lifetime of the battery. Now, car batteries like this, I think this is a Chevy Volt. I'm not sure what kind of vehicle this is here, but car batteries like this one typically have heat cycles. And so, if you heard those reports about can't charge a Tesla in cold weather, you just need to tell the Tesla or the Ford or whatever vehicle you're charging that you're about to do a charge cycle so that it'll heat the battery bank up. And once the battery is warm, no problems. So this is just another illustration of that same idea. The lithium in a charge cycle is trying to move into the anode. This is typically graphite. And if that mobility is reduced, you'll get these growths of lithium on the front of that anode that can cause penetration through the semi-permeable membrane there for the separator layer. So there are some ways we can address this. One, we want to keep our batteries within the safe charging and discharging temperatures, and those are shown on the screen for the Phi battery. The AmpliPHI and the SimpliPHI batteries have a more advanced BMS with communications, and they can actually charge under temperatures all the way down to -20°C. We just reduce that charge rate. And so those batteries will request to be charged at safe levels. And that, Daniel, what can we do with that? Why is that helpful?
It can prevent the dendrite growth.
It prevents the dendrite growth. And what else can we do with that? So what is happening when a battery is charging at cold temperatures? What's happening is there's an increased internal resistance. And that internal resistance essentially is transforming electrical energy into heat. And so if we slowly charge at cold temperatures, a fraction of that energy at really cold temperatures, it might be as high as 10% of that energy is turning into heat. But that energy, if it's coming from a solar array and you don't have anywhere for that energy to go, right, you would just be not capturing that energy. So if you start charging at low temperatures, it can start to warm the batteries up. And once those batteries warm up, you can increase that charge rate. And so we have a method of doing that in our communicating batteries that's somewhat unique to us and allows us to get a broader overall charging temperature range with our AmpliPHI and our SimpliPHI batteries. There's also temperature-based cutoffs that are built in there to keep that battery safe. And above 50 degrees Celsius, I'm not sure exactly what that is in Fahrenheit, but somewhere around 130 Fahrenheit, the batteries will slow down their output as well. So I did tell you we would talk a little bit about this. Expected number of cycles and cycle life. We often get asked, should I not charge my batteries up to 100%, as you were just saying, Daniel, to increase the overall lifetime of the batteries? Well, that is true for NMC batteries. For instance, if you have a Tesla Model 3 that is an NMC-based chemistry before they switch to LFP, it would often tell you don't charge above 85% unless you're planning to go on a long trip. Well, with LFP batteries, it's not as sensitive of an issue, and you might know that you have an LFP-based Model 3 if they tell you it's safe to charge to 100% every day, right? So on the top side, we don't see a great increase in overall life cycle and lifetime, and this is for our Phi battery, which is why it's warranting for 10 years here. But if you, on the bottom end of things, we do see a big difference. So if we're only discharging continuously down to 80% depth of discharge, leaving about 20% in that battery, we expect about 10,000 cycles out of that battery. If we discharge all the way down to 90% depth of discharge using 90% of the available energy, I believe the number is 6,000 cycles. And at 100% depth of discharge every single time, we're looking at more like 3,500 overall cycles. So it is a good practice to leave some energy in that battery. And we know that occasionally you might need to discharge down to 100% depth of discharge in the event of an outage, etc. So we have different recommendations depending on how often you're cycling a battery. If you're cycling the battery every day because you're an off-grid customer, we do recommend an 80% depth of discharge. If you're only cycling it occasionally, maybe 90% or even 100% depth of discharge is fine, because 10,000 cycles, if you do it once a day, you're looking at 26 years. 6,000 cycles, you're still looking at 18, 20 years, right? A long time. But it of course depends on the environment where the batteries are in, and we know that you won't always discharge them the way we do in the lab. So the batteries, the 5 batteries have integrated, all of our batteries have integrated breakers on them. The AmpliPHI, the SimpliPHI batteries, the 5 batteries all have 100 amp breakers on them now. All of the batteries have an internal computer called a battery management system, and that computer is programmed for cell balancing, charge discharge protection, short circuit current protection, and overcurrent protection as well. The C rate of the batteries refers to how quickly you can charge and discharge them. Most of our batteries are rated at C/2. We have a new battery we'll be shipping next month that has a higher C rate. In fact, you can go as high as 1 C discharge, meaning all of that energy, you could use all of that energy in as little as an hour in a very quick, high energy need. But for the most part, most of our customers were expecting more like 5-10 hour discharge cycles. Our batteries are designed to be scalable and expandable. So we use smaller overall battery module sizes so that we can build up our battery banks with time. And within a few years, it's quite reasonable to maybe want to add batteries to your bank. And if you have a smaller overall battery module size, it's easier to get those numbers that you're looking at to meet your needs. Daniel, what are we looking at here?
Our ability to scale. On the left, I believe that's a airport hangar in Hawaii where we've taken some of our 5 batteries, and I love those custom bus bars there. And we've scaled up these batteries, and I think that's really unique to our products, especially the 5 batteries, that we can scale these things up to meet the needs of your customers. On the right is the ability to expand. We see a system with 8 batteries there. And then we were able to come back and add 8 more batteries. And I know we get a lot of questions on how long can we go before we add new batteries to an existing battery bank. And I think, correct me if I'm wrong, usually what we say is 2 to 3 years. That's because the new batteries will in effect have the warranty life of the older batteries, and the newer batteries are going to act like the older batteries. We did have
the newer batteries are going to do a little bit more work because they have an overall lower internal resistance as well. And so if you hook those up in parallel, the new batteries will age a little bit faster, and that's why their warranty is a little bit decreased when we put them in a bank with older batteries.
Yeah. Great. Thank you, Nathan, for addressing that. I realize we only have about 12 minutes left, everyone, but we do have a question. If you want to take that now, Nathan, or do you want to wait?
Let's go ahead and take it. I did want to point out this one line on this slide is a low self-discharge rate of about 1% per month. That does mean that batteries kept in storage, right, can still be in high states of charge, which, is overall better for the battery, even over long periods of time, right? So a 1% discharge, self-discharge per month means that your battery is only going to drop by about 10-12% over the course of a full year. Daniel, you want to bring that question up?
Yeah, of course. And one thing is that on this slide is no maintenance. And that is something that historically, I get homeowners that forget to water the batteries. and you remind them, you set them up. And so that is something I think it's kind of a moot point now that everyone's moving towards these chemistries, but absolutely no maintenance is. So Mike again is asking, he has a 3.8s and a grid-tied system that are set up to supply backup loads for some small critical loads. They do what's called a mini absorb cycle, 10 minutes at 54.5 volts daily, and then the voltage is allowed to decay until the next day's charge cycle. Typically, they drop to about 53.8 before being recharged. The question is, am I reducing their life by not cycling them more vigorously, right? And I assume by that is discharging them more and charging them up. I've asked this before, but what I'm hearing today makes me a little concerned. And he additionally adds that his column counter, I'm not saying that right, the shunt, Coulomb, yeah. Thank you, seldom shows the state of charge less than 99%. So are you reducing their life by not cycling batteries more vigorously is the question.
No, I think that the answer, Mike, is that as long as you're hitting a state of charge which engages the battery BMS in the balance cycle, your batteries should be fine. Typically, that balance cycle for us, it can be, if batteries are way out of balance, it'll start at 3.3 volts per cell. You're saying there's no BMS on these, or if they're lithium batteries, there's a BMS. If it's lead acid batteries, well, the voltages are all going to be different. So every lithium battery will have some type of BMS inside them. And I'm happy to talk with you afterwards, Mike, if you want to just send an email. I'll provide my cell phone. It's a good question, and I'll provide my cell phone. You can give me a call, and we'll talk about those batteries. And I do want to make sure that you get the most lifetime out of them that you can, even if they're not our batteries. As long as they're LFP batteries, the behavior will be similar, even though the BMS might be behaving a little bit differently. So it's a good question. Bring it up afterwards, and I'm happy to talk with you.
We got a couple more questions. Let's save them to the end, Nathan.
Okay, if you don't mind, I'm going to jump through. I do want to get into the newer battery that we're leasing because I'm very excited about it. Mostly because of how we've designed it to pair with a SolArc 15K. It's an outdoor rated battery. It comes in 6.65 kilowatt hour modules. So 3 of them will make a 20 kilowatt hour stack. And so I want to get into that in a little bit. We have highlighted our PHI battery. There are thousands upon thousands of these batteries out powering houses and offices all over America. Our AmpliPHI batteries have become pretty popular, especially with the closed loop integrations with SolArc and Briggs Stratton inverters. The SimpliPHI 4.98 kilowatt hour battery is a wall hung battery. It's also outdoor rated. And those batteries, you can get those discounts for California manufacturer as well. So I'm going to skip through some slides just because I'm short on time here. But I do want to point out, if you are looking for outdoor installs, if you're in a temperate climate, meaning you don't get to really cold temperatures, where I live would be perfectly fine, Florida, places where the temperatures are warm. We get a lot of installs in Hawaii, Puerto Rico. These cabinets are a great option for containing batteries, and they're NEMA 3R rated. So both the PHI and AmpliPHI battery, if you're going to install them outdoors, should be in some type of waterproof cabinet. And these are nice options for that because they have the busing already built in. We also, if you're interested, can integrate a SolArc inverter or a Briggs & Stratton inverter directly into one of our battery cabinets. We call this an access cabinet. It's pretty much plug and play, very easy to connect. So if you're new to doing systems, it might be a good idea to start out with something like this. Again, I did talk about the charging and discharging range before. Jumping through here to the end because I want to get to this. This is our new 6.6 battery, 6.65 kilowatt hours for this battery. Overall, single battery is capable of a 1C discharge rate. That means a 6.65 kilowatt hour battery can do 6.6 kilowatts of output. That's a large power output. A 2-module stack can do over 10 kilowatts of power output. And these come in a fairly small format. The 3 stack is about 28.5 inches wide by about 6 feet tall, a little under 6 feet tall, 5.5 feet tall. And you can parallel up to 6 of these. Each 3 stack would be 20 kilowatt hours. So about 1.5 power walls worth of energy that's stored in those. It also pairs very nicely with SolArcs, etc. If you are doing parallel banks, you'll want to make sure above 2 parallel banks to use a combiner, and we recommend the use of DC breakers and fuses. With a SolArc 15K, you can actually use the battery bus bars as a combiner. They have dual input breakers on that SolArc 15K, which make it a very easy system to utilize these battery stacks with either a single stack or two battery stacks. So again, excited to introduce this with the SolArcs as well as our own inverter. It's exciting for us to release this new battery lineup. We have put together some packages to help you understand how much overall backup time that you will get. And so if you're using your loads, about half of the loads that you would typically do for a small system like the one on the right, 50% of the loads might be in your critical loads panel. And we're expecting a overall backup time just with a single 6.65 kilowatt hour battery of about 11 hours for your house. That's a nice amount of time, and it's you can of course expand your battery bank to be larger than a single battery. If you're trying to back up a couple of, maybe 75% of the home with something like a SolArc 12K, we're expecting a little over half a day, 14.5 hours of backup time. With a SolArc 15K, most customers back up everything in the home. And so if you're backing up everything in the home with a single 3 stack of batteries, we're expecting about 16 hours of storage, or you could easily double that with 2 stacks. And so we've got these package deals available. So I'm going to try to save some time for questions here at the end. So both the Boss 6 and the Boss 12 cabinets are outdoor NEMA 3R rated, and you can go all the way up to 140 kilowatt hours with those Boss 12 cabinets if you're interested. So I want to point out for the newer battery, we have both floor mount and wall mount options available for it. And so you can mount this on a wall, or you can bolt it down to the floor. There is a rack that goes behind the battery to secure it. And that's especially important in locations like where I am, sure, earthquake zones. It's also very nice in that this battery is stackable. All of the communications, as well as the electrical contacts between batteries, are made in this patented system that we have for stacking in those connections. So it's called Rapid Stack, and you can see those electrical connections are made here, as well as all of the communication made right here. Lastly, before we jump into questions, I do want to highlight we have an Elite IQ installer program. That's an Elite installer qualification program. We have many installers that are on our maps, but we would always like to get more. So if you're not on our map, we want to highlight that it gives visibility to our customers, to your company if you're an installer. So please do reach out to us if you're interested in becoming part of our IQ program. We also give $100 cash back per battery installed. And I believe right now the marketing team is advertising 150 cash back on the AmpliPHI, the PHI, and SimpliPHI batteries. So we have a questionnaire for you as well. If you want to try to highlight how we can make these trainings better, please let Daniel or I know by filling out the survey. Again, I'll send you that QR code. I'll send you the links. So you'll get the slide deck from us. So if you're here for those NABCEP credits, our email's on the screen, energystoragetraining@basco.com. Send us an email. Tell us how your name should appear on your certificate. We'll check the attendance logs and we'll get those issued. As well, if you'd like to talk to one of our application engineers about a project that you have, or if you want to talk to Daniel and I, the phone number is there. Feel free to reach out to us. Daniel, let's jump into those Q&As.
Yeah. John, welcome, John. Good to see you again. He's asking if a battery management system fails, can it be replaced without having to be shipped back to California? And so, Nathan, maybe we don't want our average person opening up a battery with a lot of potential for current there, and maybe is the battery management system the most likely mode of failure? Those last two comments were mine.
Yes. So Daniel and John, thank you for the question. The answer, unfortunately, John, is that because of the safety risks of opening up a battery and the huge overall potential current there that could cause injury. We do not allow field replacement of our BMS units. However, I will say that I never hear about our BMS units failing. It's a very rare occurrence if the BMS fails. If you are having problems with a battery, most likely it's another culprit. It doesn't necessarily mean that the BMS can't fail. It's just not a common occurrence for us. The BMS units that we put, especially in our AmpliPHI and SimpliPHI batteries, are Cadillac designed BMSs that can probably handle a lot more power and current demands than we're currently putting on them. But the answer is no, sorry. Daniel, other questions, please? And thanks,
of course.
John.
Yeah, and again, reminder everyone, if you're looking for knapsack credits, please email energystoragetraining@basco.com. I got somebody asking is that they work in off-grid, solar, and battery microgrids. As such, the batteries could be expected to be charged and discharged every day, sometimes multiple times a day. What recommendations do you have for discharging/charging to optimize battery health and lifetime? I think maybe we could talk a little bit about depth of discharge and the rate at which we charge the batteries.
Yeah, absolutely. So there are a lot of considerations that go into how quickly you charge and discharge batteries. Also, depth of discharge is quite important. So if you are discharging, daily or multiple times a day, we recommend that you don't go below 20% state of charge, meaning discharge your battery all the way down, but leave 20% in, at that bottom side. So you're using 80% of the available capacity. That does, of course, mean that you'll need maybe an extra battery. If you have a 5 battery system, if you're only cycling to 80% depth of discharge is equivalent to 4 batteries, right? So there's an added cost of doing that, but we're expecting more than double the number of cycles as opposed to 100% depth of discharge. So I would recommend not going below 20% depth of discharge. We don't seem to see a big increase on shallower cycles than about that 20%. So going down to just 50 would probably not increase, the value of that system. Additionally, on the charging rate, if batteries are cycled repetitively many times in a row, so let's suppose I've got a generator system that kicks in and charges the batteries when they go down. If I've just discharged my batteries at a high rate, and then I charge them at a high rate, and then I discharge them at a high rate, the temperature inside the batteries builds up. And with time, higher temperatures can lead to degradation of the electrolyte inside the cells themselves. And so we encourage you to reduce that charge rate maybe a little bit, even just a C/3. So it's a 3-hour charge cycle instead of a 2 would be one recommendation. And if you're charging off of solar, that would be equivalent to having, a slightly larger overall bank compared to your solar array.
That's all the questions.
Gave you some ideas. We're, happy to talk more about it.
That's all the questions we have. And thank you, Nathan, for the great talk today. I do want to remind everyone, if you need your knapsack credits, energystoragetraining@basco.com. Stay tuned. Next week, we're going to be talking about NEM 3.0. Although that is specific to California, we're seeing this kind of net billing tariff as opposed to net energy metering coming across in other parts of the country. So Nathan, please close us out with some final thoughts on Battery Chemistry 101.
Well, thank you, Daniel. I think the biggest point I want to make, even if you decide to install NMC batteries, in terms of chemistry, at least know what you're installing, right? And if you are installing a less safe battery chemistry, make sure you're taking the appropriate precautions as to where you install that battery, parking ballards, that kind of thing you're putting in a garage. Follow that NMC code, the NFPA, and make sure that you're keeping your customers safe. I think that's the biggest thing overall with battery chemistry, that and lifetime. And ideally, you switch to an LFP chemistry. I know there are a number of options, not just us out there now. And LFP chemistry is really what you should be using on home battery and storage. So thank you, everyone. We really appreciate your attendance. And if you're interested in that 6.6 battery, I'll provide a link in the email when I send out the slides later.